Ladies and gentlemen and distinguished guests, and I know there are several H. Bolton Seed lecturers and other lecturers here in the audience today. It really is a great honor. It's almost overstated a little bit. The use of the word honor is used perhaps too often, but in this case it really is. I was a student at Berkeley, as Gary mentioned, and Professor Seed was in his heyday as a professor there at the same time. And although Professor Seed was perhaps best known for his research on geotechnical earthquake engineering, he was also, as some of you know, an unbelievably good teacher, stunning, amazingly good. And when I arrived in Berkeley, I was really overwhelmed at the quality of the teaching. And Mike Duncan's here as well, not just Harry Seed, but his lectures just flew by in a way that I've never experienced since, really, with anyone else. So it's really a little bit surreal to be here today, giving the lecture in his name. I've put up a picture here of the Cal Berkeley logo, which of course was where Harry Seed made his name and where he stayed for many years. But it did make me reflect just briefly on the universities that I have had connections with since I've been in the United States. And I have had an associate professor's position at CU Boulder. They have to call themselves CU because the UC has already been taken. And at one time I was also on a sabbatical in Princeton. And it kind of occurred to me that these are all rather fierce-looking animals, these mascots. So when I ended up at the Colorado School of Mines, anyway, he's got some dynamite in his mouth, which is sort of a little bit, no one's ever explained it to me properly. Anyhow, I'm very pleased to be here. You know, when I arrived in Berkeley, Harry Seed looked like that, and unfortunately I looked like that. And but nevertheless, Professor Seed was extremely accommodating. I was his teaching assistant for his 270A class that was a staple of the large graduate program in those days. Just one other anecdote, if I may. I visited Berkeley. In fact, the last time I saw Harry Seed in Berkeley was with my late wife, Valerie. And we visited Davis Hall, where Harry Seed had his office, on the day of a very significant earthquake by the standards of the Bay Area in those days, 1979, August the 6th. Incidentally, that's the same year that Harry Seed gave the Rankine lecture in London. And I was on my way to Davis Hall, and I was in an elevator going up to the 4th floor. And when the doors opened, people ran into the hallway. There's been an earthquake, and I'd missed it. And to this day, I've never felt an earthquake. And it was fascinating because Harry Seed and Mike Duncan took us to lunch that day in the faculty club, and it was quite an occasion. When I got back to the faculty club where my wife was staying later, she said, I forgot to mention it really. She said, was there an earthquake? I saw the paintings swinging on the walls. So anyway, that was a remarkable day. So it was the largest earthquake, apparently not since 1906, but 1911. At least that's what it says in this San Francisco Chronicle cutting. All right, now to the business of the ranking of the Harry H. Bolton Seed lecture. I might add, my wife worked in Bolton, Lancashire for many years too, which is a suburb of Manchester. I'm going to talk about the use of finite elements in the modeling of variable soils and the power of the finite element method, and also talk a little bit about how the finite element method can be applied to risk assessment methodologies and has a particular advantage over some other methods. Here we have a couple of slopes, both with the same factor of safety of 1. They both failed, but clearly one has much more significant consequences than the other. And here straight away is one of the benefits of bringing in a risk way of thinking. The probability of failure, weighted by the consequences of failure, is the definition of risk. So one can tolerate higher probabilities of failure if the consequences are low. There's few engineering materials, I think, that are more amenable to a probabilistic treatment than soil and rock. I'm on the Geotechnique panel nowadays, and looking at volume 1, number 1, they got someone called Karl Terzaghi to say a few words in the preface, and it's interesting to see how he highlighted in my red font here, the properties of materials may vary from point to point. This is what makes soil complicated stuff compared with other engineering materials. And incidentally, the same year, a very influential book, I think, by D.W. Taylor was published, where in his introduction, he also drew attention to this inherent difficulty in geomaterials. How do you model these things when the properties are varying all over the place? So actually, it's only fairly recently, well, in the last 20 years or so, that people have started to try to model explicitly this variability that Taylor and Terzaghi drew attention to all those years ago. What you're seeing here is a finite element analysis of a bearing capacity problem, where the soil has been modeled as a random field with variable properties based on a statistical description. It's a little bit more about this method later. The dark and the light zones refer to a whole spectrum of strength parameters. It's funny, when you have a random material or a variable soil, quite rarely do you get the classical symmetrical mechanism that you would see in textbooks of Terzaghi's bearing capacity theory. It nearly always goes one way or the other. Anyway, here's an outline of my presentation. I'm going to talk initially about slope stability by finite elements, which seems to be a growing topic of usage in practice and academe. And I'll make a few observations about perhaps the benefits of a slope stability approach by finite elements. And then maybe slightly out of context, but something that's interested me recently, the growth of LRFD as a way of dealing with variability, but factoring the loads and resistances differently. Maybe you have more than one factor of safety going on at the same time. I will briefly review risk assessment tools in geotechnical engineering, but we won't get too deeply into them today, but I will summarize what I call 3 levels of probabilistic analysis, and then some concluding remarks. So let's move on. What is slope stability by finite elements? Well, you design a finite element mesh to represent the geometry of your slope, which could be quite complex. And we apply some gravity loads to that slope based on the unit weight of the soil. That's a fairly standard algorithm in finite element programs. We'll have a very simple stress-strain law, elastic, perfectly plastic. The perfect plateau is governed by Coulomb. And then we'll do an elastic analysis initially. Forget the plasticity, forget Coulomb, we'll just do an elastic analysis. And we'll look at each element to see if they have violated Coulomb. So we have a little function called m. If m is negative, we're in illegal territory, and we shouldn't really be there. If m is positive, then we're still elastic, and probably things are okay. So if an element is violating Coulomb, we're going to turn on a little stress redistribution algorithm that will sort of move the stresses around a little bit. And brother, can you spare a dime, really? Offer the stresses to the neighbors and ask them to pick it up. And in their turn, it may cause them to violate Coulomb if they pick up some load from the neighbors. So this is an iterative algorithm. And it may take quite a few iterations for everything to settle down, for all the elements to satisfy Coulomb, and of course, equilibrium all the stresses can be moved around, but they must still satisfy equilibrium with gravity. To find the factor of safety, we'll use a strength reduction approach, which means we gradually weaken the soil by dividing by an ever-increasing strength reduction factor until nodal displacements in our mesh rapidly accelerate. And when this happens, along this top axis here, you'll see the strength reduction factor being increased. At some point, something pretty critical happens. The displacements magnify very quickly. And at that point, the strength reduction factor is the factor of safety. And this is the same definition of the factor of safety that is used by Bishop or the ordinary method of slices or any other method. It's just come at it from a slightly different direction, but this is the same factor of safety. One of the benefits of the finite element method, I think, for slope stability is that it seeks out the critical failure mechanism. It finds the weakest path through the soil where the strength is unable to satisfy the stresses that are being asked to support. The user doesn't have to, in advance, anticipate where the failure mechanism will be. The critical failure mechanism comes out of the analysis automatically. We can see some other interesting examples. This is a layered soil in which we did strength reduction. 3 different undrained clay layers. And here, in fact, we have 3 mechanisms all occurring with the same factor of safety. And I just asked on the right whether a traditional limit equilibrium approach would be able to find all 3. I wonder if you were using limit equilibrium, you might find one and think that was it. It's just, but even if the limit equilibrium method could do this, and I'm sure you could with sufficient search, this comes out naturally from the analysis without the user having to tell it where to look. So what hope is there for a random field then when we're trying to find the stability of a slope with highly variable soils varying according to some statistical distribution? I think a numerical approach is essential for this kind of complex problem, where we have circular and planar type failure mechanisms and also some curious, little berm type failure up here. One thing also about the finite element approach which I find intriguing is how robust it is. Even coarse meshes, while coarse meshes don't give you quite such a nice failure mechanism as a fine mesh, they all give very similar factors of safety, and this is a benefit. I think the user doesn't have to worry about mesh design quite as much as you would imagine. Certainly other methods, for example, limit analysis methods, do have problems sometimes with mesh design. So just to summarize then, what I believe are the advantages of the finite element approach for slope stability is we don't have to make any a priori assumptions about the shape or location of the failure mechanism, of the critical failure mechanism. It's been numerous times we've validated it against limit analysis, limit equilibrium, and chart solutions. I think you'll find it's a standard feature of many codes now. Familiar names often have a slope stability module. You might even be able to buy it separately from the rest of it. And if anyone's interested, you can download a very powerful free one from my website. You can contact me later if you're interested about that, in having that. A couple of other quick examples just to show where I think we can benefit from the finite element approach. 3D slope stability analysis. And my apologies to one or two of you who've seen this one before, probably. But, 3D slope stability analysis is rarely performed. And I think there are 2 main reasons for that. Limit equilibrium methods become pretty messy in 3D. Methods of slices become methods of columns. And imagine the mess we get into with side forces and all that stuff. In a finite element approach, I think it's more of just a third, if you're into Fortran, a third do loop would get you to 3D from 2D. The other point I think that is more or less a received wisdom is that 2D is generally thought to be conservative, on the safe side. So why bother, go to all that trouble? My point in this 2 or 3 slides here is just to emphasize point 2 a little bit. I think 2D is conservative, so long as the most critical 2D section is selected. And that may not be obvious. That may not be entirely obvious. Which is the best 2D section, the most conservative? To look at this, we set up a rather contrived problem here. A slope with a diagonal layer of weak soil running from top left to bottom right. And ask the question, which is the critical 2D section for this particular problem? Maybe it's one of those, just going right across the section, perhaps. Or maybe even the one right down the weak zone. A little bit flatter, that slope, but entirely weak. So we ran all these by finite elements. A 3D, and by the way, there are 3D programs available for download if you're interested. A genuine 3D slope strength reduction approach gave us a factor of safety of 1.52 for this slope. So if I may, I would like to call that the factor of safety of this slope, 1.52, based on our usual understanding of a factor of safety. On the next slide, we show the comparison of the 2D results with that 3D result. This V-shaped thing, if you look at the y-axis, that is the factor of safety, not this axis. Along the x-axis, it's y, which is those sections passing from left to right. We can see that those simple sections were occasionally on the unsafe side compared with 3D. The 2D gave a higher factor of safety if they were out at the edges than in the middle. I suppose some people would naturally say, well, only a fool would take a 2D section out on the edges where all the soil is strong. I accept that. So the 2D section is safe in the middle. The 2D section right down the weak zone with a flatter slope was tremendously conservative. I think even by our standards, we would have thought that was overdoing it a bit. But the truth is, 2D sections are conservative so long as we choose them carefully. And that may not be always obvious. Another game we can play with the finite element approach is to ask a slightly flip question about how long is an infinite slope? How long is infinity? Well, I think teachers of geotechnical subjects love the infinite slope because it's a nice closed form solution. It's the only slope, I think, that has a formula, right, for Fs equals. And there it is on the right, there's the formula. And if we take a particular case, let me actually choose some properties. If I fix the properties and the slope angle as shown here, actually we will get a factor of safety of 1.15 by using the traditional infinite slope equation. So let's have another look at this with a finite element model of a long slope. How long is long is the question that we're trying to address here. L is this width down here at the bottom of the figure, and H is the thickness of the soil. So we just ran a few problems with different L over H's. Remember, the infinite slope gave 1.15 as a factor of safety. So as we increase this, for a fairly short, stubby slope, we got a factor of safety of 5, which looks pretty circular, doesn't it? And then if we lengthen it a bit, twice the length, the mechanism's still pretty circular, and a lot higher still, 2.9, but coming down. If we lengthen it further, we're starting to get the translational type mode of failure, which is, of course, central to the infinite slopes equation. And then I'm giving up after 8, so don't worry, there's no more, but the 8, L over H of 8 is now starting to resemble at least a translational failure. But the factor of safety is still quite a bit higher than the infinite slope. Here is a summary. The horizontal line is the infinite slope solution, and here are the finite element solutions with increasing L over H. So we can see we can conclude a couple of things, which probably not exactly new, but infinite slope equation is conservative. You're on the safe side for sure if you use it. And it seems from this figure, at least for the particular properties that I chose, that when you get to about L over H of 20 or more, we're roughly in the ballpark of using an infinite slope equation without it being too conservative. Okay, part 2 of my presentation is just a few words on load and resistance factors. I think the geotechnical community have sort of realized that this is something that may be here to stay, where we increase the loads by some factor to be on the safe side, and we reduce the strengths by some factor to be on the safe side. But we can tailor those factors according to how much we know about the various aspects of the design. So it's certainly a logical approach, but I suppose there's some dismay at the plethora of factors compared with the nice world where we used to have just one. Really, it's that one factor of safety I want to just look at quickly here. I've taught soil mechanics and foundations quite a few times over the years. And you know, slope stability problems have a factor of safety 1.5, and bearing capacity problems have a factor of safety of 3. What's that? Never seem to say anything except in Duncan and Wright's book. It's about the only place where this is explained slightly. But my question then is, does this mean we design foundations to be twice as safe as slopes? Well, obviously, the answer is no. These factors are quite different. These factors are not the same animal. They cannot be compared directly. One is a load factor, the bearing capacity one is a load factor, and the slope stability one is a strength reduction factor. And I think that's something that needs to be emphasized more in textbooks nowadays. But the slope stability one, I mean, we can easily see that it's a strength reduction factor. Here I've just taken the ordinary method of slices just for illustration. Here's the formula, the summation if you're doing the slices. If you want to make the factor of safety equal to 1, you just divide both sides by the factor of safety. And that means that we have a strength reduction factor. We have to reduce the strength by Fs, and we have to reduce the cohesion and the tangent of the friction angle by the factor of safety. So this is obviously a strength reduction factor of safety. On the bearing capacity side, however, if we just take a typical strip footing and Terzaghi's bearing capacity equation, we could calculate the ultimate bearing capacity using that formula, and then the allowable value is related to the ultimate value by a factor of safety, which is a load increase factor of safety. And what we're saying here at the bottom of this slide, is that in order to cause a bearing capacity failure, we'd have to increase the allowable loads by 3, typically, for a factor of safety in bearing capacity. This made us wonder a little bit about why this evolved this way historically in soil mechanics and geotechnical engineering. Why can't we do slope stability by load increase instead of strength reduction? Well, we can do it quite easily in a finite element or a limit equilibrium approach for that matter. Here's an example where I fix the cohesion and the unit weight and the slope angle and the height, and I'm going to vary the friction angle a little bit, but we'll see that in a minute. I'm going to bring the slope to failure by increasing gravity rather than reducing the strength, which is the traditional way of doing it. I'll have to give slightly different notation to the two. The factor of safety with a subscript C tan phi is the strength reduction factor, which is the one we always do. It's the traditional one. And the gravity increase factor of safety, I've called that Fs subscript gamma, because the unit weight is being increased. Well, here's the result of a number of runs. Along the x-axis, we have the traditional factor of safety, and along the y-axis, we've got the load increase factor of safety. And we can see that it's a function of the friction angle. The relationship between these two depends on the friction angle. There's a couple of things to note here. The only time they're the same is if it's an undrained problem, and the friction angle is 0. So that's the bottom left-hand point. The other thing I'd like to draw attention to is that a factor of safety on strength reduction of 1.5 for a friction angle somewhere in the low range is about the same as a factor of safety on gravity of 3. The 1.5 and 3 seem to be related and almost meaning the same thing, except by different approaches. You notice this line, this plot is getting very steep to the right. The 30-degree angle is getting pretty high on the right-hand side. Well, there's a couple of observations we can make here. Firstly, the factor of safety on the strength reduction is always less than or equal to the factor of safety on gravity increase. And maybe this is a good reason why slope stability analysis was never evolved with a gravity increase approach. If the friction angle is greater than the slope angle, you can never bring it to failure by gravity. It will just always be safe. So this line is actually tending to an asymptotic result at 33.37 degrees, which is the friction angle of the slope angle. So that's a good reason for not doing gravity increase, I think. On the other side, let's have a quick look at bearing capacity by strength reduction. Why don't we do that? Why did it not evolve in that way? Well, to make a point here, I'm taking the Terzaghi bearing capacity equation, and I'm taking a bit of a liberty here, but I'm just taking the first term of the bearing capacity equation, which is, a little bit naughty, but the conclusion I'm going to reach is the same whether I include all terms or not, so it just makes life a little simpler. The bearing capacity factor, NC, down here, is classic solution. It's a Prandtl solution. It's a closed form equation. Here it is. NC depends on the friction angle, as do all the bearing capacity factors for that matter. And you can see that NC depends on this rather interesting formula involving Kp and tan phi. So let's look at Kp. I think most people use this version. Do you teachers out there? Tan squared 45 plus phi over 2. But if you like trigonometric identities, that's also Kp, and that's also Kp, and that's also Kp. And I'm not satisfied yet. There's one more that we dreamt up in an obscure conference paper quite a few years ago. What I like about this version, and I'm not expecting this one to catch on in undergraduate soil mechanics, but what I like about this one in red is that it depends on tan phi only. So we've kind of isolated the tangent of the friction angle, which really is the fundamental variable in Coulomb's equation. And we've managed to write the bearing capacity of this footing as an explicit function of cohesion and the tangent of the friction angle. I haven't included all the mathematics here, but it's not too messy. But here is the bearing capacity equation written with our new look Kp factor. And we can see that Q ult, the ultimate bearing capacity, depends on C and tan phi. So we can do strength reduction analytically on this and get some formulas to plot. And we can compare the two factors of safety like I did just a few minutes ago for a slope. So here we go. Here's the result we get. The equations are published elsewhere if anyone wants to follow it more closely. Again, the friction angle matters. It affects the relationship between the strength reduction factor of safety and the load increase factor of safety. Of course, the load increase factor of safety is what we normally do. That's the traditional approach. you can see once more that a factor of safety on strength reduction of 1.5 is about the same as a factor of safety on load increase of 3, now called Fs subscript Q. What this seems to be telling us is really these two factors of safety are really telling us pretty much the same thing, just coming at it from different angles. The same level of safety is implied for a factor of safety on reduct strength of 1.5 as a factor of safety on loads of 3. It does also tell us that strength reduction factors are more influential. A design is more sensitive to strength reduction than it is to load increase, which may have implications for some of these tables we see of load increase and strength reduction in the codes. By the way, we could come to the same conclusion with the other two bearing capacity factors. They give very similar results. All right, so part 3. How are we doing? Let's see. Good. Right, so we talked earlier a little bit about finite element methods being good for variable soils, seeking out the failure mechanisms naturally. So this should be an important tool for us to use if we want to do a risk assessment. But first, let's just define the goal of a probabilistic geotechnical analysis. I think fundamentally we're trying to calculate the probability of failure as an alternative, or more likely, a complement to the factor of safety that is traditionally used. I know there's lots of different terminology out there. Some more optimistic types prefer to use terms like reliability, and maybe probability of design failure doesn't sound quite as bad as just probability of failure, which is a little bit dramatic. Certainly if it's a dam sitting above a large city, that would be a probability of failure. If it's a traffic light phasing down International Boulevard going out, you might call that a design failure. Reliability is typically just 1 minus the probability of failure. So probability of failure can never be less than 0 or greater than 1, and the reliability is just 1 minus that number. Reliability index is a little bit more obscure. It's based on standard deviations and so on, but we won't worry about it too much. So here's an obvious question, I think, just to get started. Since we're trying to replace or at least complement the factor of safety with a probability of failure, what on earth is the relationship between the probability of failure and the factor of safety? It seems like a logical question to ask. And for that, I turn to a very well-known example that I'm sure many of you have seen before. Let's take a couple of slopes, traditional uniform slopes. Here I've got the cohesion and the geometry is the same in both cases, but one has a higher friction angle. And if you go to charts or limit equilibrium, you'll find that the example 2 gives a higher factor of safety than example 1. No surprise there, it has a higher friction angle. So slope 2 is safer, right? Well, you probably already guessed this is a trick question, right? Now somebody annoying comes along and does a probabilistic analysis and says, hey, wait a minute, these two sites where you have your slopes are quite variable. And site number 1 has a certain variability of soil strength, and site 2 is even more variable. And in fact, after some analysis, this individual has come up with some statistical descriptions of the factor of safety that says the mean factor of safety of the first example was indeed 1.5, which is what you found out earlier, but it has a standard deviation, which is a measure of the spread of results of 0.18. And example 2 has a mean factor of safety, which is indeed 2, which is what you came up with earlier, and a standard deviation of 0.5, rather higher. Well, let's plot these things as normal distributions. I'm pretty sure we've all come across the normal distribution, which is the symmetrical bell-shaped curve. And there are many other distributions out there, but let's keep it simple. The blue line is slope number 1, and the pink line is slope number 2. If these things are drawn properly, the area underneath the distribution equals 1. So that makes it very convenient for calculating probabilities as areas under the curve representing the range you happen to be interested in. Well, you can see what's coming, probably. The probability of failure is the area of the curve to the left of the factor of safety of 1. This is failure, Fs less than 1. And if we look at a little detail of that bottom left corner, you can see what's going to happen. The so-called safer slope has a smaller probability of failure, that area, than the safer slope, which has a larger area. And so we've got this contradictory result that the safer slope has a higher probability of failure. Now, this is a pretty depressing thing to show everyone. I don't want to put you off doing this stuff. But this is just something to bear in mind, that direct comparisons, and I feel quite strongly about this last statement, direct comparisons between the factor of safety and the probability of failure is to be discouraged. They are not the same thing. And for a start, the factor of safety is based on one number, the factor of safety. The probability of failure is based at least on two numbers, the mean and the standard deviation. And I know a lot of papers are written where this final sentence here is not being discouraged enough. The definition of risk I touched on earlier, right at the beginning of my presentation actually. It's the probability of failure weighted by the consequences of failure. And just down the road from me in Golden, Colorado, I have the Bureau of Reclamation, who are responsible for hundreds of dams in the western United States mainly. And they define risk as a three-step formula. It's the probability, P for probability, the probability of some critical event occurring, maybe an earthquake or a severe rain, weighted, I suppose the times means weighted by the probability of system failure, given that the event has occurred. It doesn't always follow that you'll have failure. And we know about San Fernando, just hung in there, right? Finally, weighted by the adverse consequences given the failure, and that would be measured in terms of loss of life, infrastructure costs, or a combination of both. What is acceptable risk? And I know J.L. Wright is interested in this topic very much here at the front. It's not for me to get involved in this one too much. It's very site-specific. Depends entirely on the kind of project that's being considered. This is a classic graph from Becker in 1982 that has appeared in many other incarnations since then. But the same idea, the general idea is still as true as it ever was from 1982. Along the x-axis, well, at the top of the, if you like, the top x-axis is lives lost. The bottom x-axis is cost in infrastructure, I suppose, in 1982 dollars. And up the y-axis we have the, if you like, the acceptable annual probability of failure. So the black lines sort of imply the division between acceptable and unacceptable. And I suppose some people have looked at Katrina and New Orleans and after the event, of course, and decided that the levies in that event were, at the time, in the unacceptable range, given the risk to human life. How do we do a probabilistic analysis, though? How do we actually calculate the probability of failure, and therefore the risk? Well, I have three levels here, which I'm going to touch on briefly. The first level is really the one that's used in practice. This is the state of practice called event trees, where an expert panel get around a table and thrash out some probabilities for a design. I'll show you a quick example of that. Another step up in terms of a little more mathematical, but something that's absolutely doable on a laptop in a few seconds are the first order methods. I'll give you a quick example of that. And then finally, there's the whole family of Monte Carlo methods where you just crank the handle over and over again, repetitively calculating something until statistics settle down of whatever it is you're trying to find. event tree, and I'm grateful to Suzanne Lacasse for one or two of these slides. There's a Rankine lecture from 2015. I borrowed this from her. An event tree is a graphical representation of many chains of events that might result from some initiating event. Some of the chains may lead to failure, but many will not. And the branches are, I suppose, so-called because off each node you get branches and more branches coming off those branches. And each branch represents some event that might happen. A more detailed example here might involve some earthquake triggering this whole thing with a low but not a negligible probability circled in the red dashed lines. And then the panel will get together to try to decide what things could go wrong and what are the probabilities of those things going wrong subsequently. For example, the gates might be closed and inoperable with a probability of 0.1, and then there might be some loss of reservoir control with a high probability of 0.7, and then if the reservoir is full at the time, or what's the probability of overtopping. One thing about all the branches coming off a node is that the probabilities must all add up to 1. We must cover all possibilities. Finally, you can predict a probability based on the product of all the individual probabilities on the tree, on the path, the bad path that leads to failure. These things can occupy many pages of reports. You sort of unfold. These branches can go on for quite a long way. Level number 2. These are involve some mathematical calculations. They're very easily done on an Excel spreadsheet, for example. I have just about all the programs I'll mention in this lecture are available on my website for download for anyone who's interested. This is coming back to a bearing capacity problem, for example. Let's make the cohesion and the tangent to the friction angle random variables. So here at the bottom, you see I've made the mean, I've given the cohesion a mean and a standard deviation, and I've given the tangent to the friction angle a mean and a standard deviation. Let's assume they're normal distributions, which is the simplest assumption one can make. And just to add a bit of spice, let's assume that these parameters, C and tan phi, are actually negatively correlated, which is to say they're not entirely independent of each other. A negative correlation implies that when tan phi tends to be higher than its mean, the cohesion will tend to be lower than its mean, and vice versa. That's a controversial assumption. Some people believe it, and I'm happy to bring it in for this demonstration. If the allowable bearing pressure that we're designing this thing to is 300 kilopascals, let's say, then I suppose the probability of failure should be defined as the probability that the bearing capacity falls below 300. What is the probability that the bearing capacity will be even less than the allowable bearing pressure, including a factor of safety of 3 or more? The first order reliability method, which is what I'm discussing now, is really an optimization method. If you consider 2 random variables, instead of a single normal distribution, you get a hill, right? It's the 2D version. And the top of the hill represents the mean values of those variables. And as you get out into the tails, the probability of those variables occurring are much, much smaller. There is actually an infinite number of solutions that might cause the bearing capacity to be less than 300. The cohesion could be exceptionally low, or the tangent of the friction angle could be exceptionally low, or both. But you know, as you get out into the tails of this thing, we're very unlikely, if I can find the mouse, values out here are extremely unlikely because they're right down in the areas are extraordinarily small. We're much more likely to have values up here, near the top of the hill. So the first order reliability method, oh, by the way, the red line is the locus of all values of C and tan phi that would cause a bearing capacity of 300. What the form method does is it finds the most likely combination of C and tan phi to cause failure. And the most likely ones are the ones with that yellow arrow, the ones closest to the top of the hill, because they're the most likely to occur, and that's what form will deliver, FORM, first order reliability. Looking down on top, you can perhaps see that line, that locus, that solid black line, and we're interested in the point that's closest to the top of the hill, sometimes called the design point, but I don't like that name much because no one's going to design something to fail, but that is the point that the method will deliver. It's called first order just by the way because it approximates the solid black line by a linear function at that point, which I've exaggerated here a little bit. Quite often, I'm yet to find a problem where that linear assumption is bad, is worrying, but I've drawn it rather more exaggerated it here to emphasize the difference. If you go to, there are plenty of proprietary codes that you can buy to do this, but here I've set up this very problem using my own in-house version. The yellow numbers are the ones that the user would supply. The yellow numbers are the input. And without getting too bogged down in it right now, I'm happy to show it to anyone later, but if you use the solve function in Excel, which I'm sure many of you are familiar with, we can optimize this, and if I run the solver, then in a moment, a few seconds later, you will get a probability of failure and a reliability index. By the way, those are uniquely related. The glass is half full on the left and the glass is half empty on the right. So form does a little optimization with some restraints and constraints. The level 3, so this is the final part of the discussion of risk assessment methods. A vast topic. Monte Carlo will get you there eventually. You just hammer away, repeatedly calculating something until the statistics of the thing you're calculating start to stabilize. And at that point you say, okay, we've done enough, and we can stop. Again, I've just set up a quick Excel spreadsheet just to solve the same bearing capacity problem that we solved a minute ago using first order reliability. By the way, we perhaps ought to just make a mental note of the result of 0.21% here. That's the result we got in the optimization program. Here I've got exactly the same data, the same yellow input, but now I'm using Excel's own random number generators to generate random values of C and tan phi. So, there's various ways of doing this, but initially in this case, I've generated a standard normal with a mean of 0 and a standard deviation of 1, and then I've shifted it to the actual mean and standard deviation of the cohesion and the standard deviation. If you're interested in these formulas, you come and see me later. So essentially, we just grab a cohesion and we grab a tangent of the friction angle from their random distributions and plug them into the Terzaghi's bearing capacity equation. And we calculate a bearing capacity. Then we do it again. Grab C and tan phi, different values every time from their random distributions. On the right-hand column, I'm just checking that my correlation is working, and it's always prudent, at least at the very bottom of your column of numbers, to check that the mean and the standard deviation of the Monte Carlo generation is indeed what it should be. For example, I did 100,000 repetitions here, which is probably overkill. I got a bit overexcited there, but yeah, so the cohesion mean is 3.99 and it should be 4. The standard deviation is 1 and it should 1.0. So it looks promising. I'm checking the tangent of the friction angle here. It looks about the same as the yellow numbers, and then the cross correlation should be minus 0.3. So it's always good to see, it's always worth checking that those random numbers are indeed reproducing the distribution that you entered in as data. So here's our Monte Carlo simulation. So each line corresponds to, if you like, a conventional Tertsagi's bearing capacity calculation. In the right-hand column, I'm just checking if any of these bearing capacities fall below 300. Not many of them do, but every now and then one does, like this one. You see 270.7. So I put a little 1 in that column if the bearing capacity falls below 300. And then at the very end, I add up all the ones. You can't see many in this truncated list. And we get, in this case, we've got about 212. We divide that by the total number of simulations. It's as simple as that. And we get a probability of failure of, well, 0.21. I didn't cook it, it just got the same. Really what this tells us is that the form assumption of linearity was a good one, and we got the same result. If the form assumption is bad, though, for whatever reason, then the Monte Carlo is the way to go, because there's no assumptions, really. We just hammer away and get an answer. It'll get there in the end. This is the problem we just solved when showing little black dots for all the cohesions and tangents of friction angles. The black line is the locus of the failure. So any dots that lie below the black line indicate failure, and any dots above the black line indicate that it didn't fail. You can see the role of the cross-correlation very clearly. It's like an Andromeda's galaxy, isn't it? Sort of as the correlation orients this ellipse. If positive correlation actually is more conservative, positive correlation leads to a higher probability of failure, actually. And so if you don't know anything about the correlation between cohesion and tangent of friction angle, you might be well advised to make it positive to be on the safe side. Anyhow. All right, so finally, just a few slides about a more sort of research-oriented approach to probabilistic geotechnical analysis. This methodology was developed in the sort of mid-90s, in the last century. It's not that new. And it really was based on random field generation theory, which has nothing to do with geotechnical engineering. It's just a way of generating a random field spatially. But then we were working with Gordon Fenton from Dalhousie University, who was a student of Van Mark at Princeton. We then mapped the random field onto conventional finite element programs, and we combined the two methodologies. And then you do Monte Carlo. One thing that this method does that none of the methods I mentioned previously does at all is it takes account of spatial correlation, which is really to say, if I drill two boreholes in opposite corners of a field, the property I measure is less likely to be similar than if I drill two boreholes close together. There's a spatial trends in the ground, especially in stratified soils, of course, much stronger correlation horizontally. This random finite element method can take account of that spatial effect. All the programs are open source, again, as I mentioned earlier. And actually, the programs have been incorporated in one or two proprietary codes now as an option for those people that want to do this. We have rediscovered many different applications within geotechnical engineering using this method. Settlement, or in particular differential settlement, is a very interesting topic, where in this case the gray scale, the white zones mean more compressible and the dark zones mean less compressible. These are all published. Bearing capacity, seepage. We get wobbly flow nets, of course, when we have a random permeability. I often joke with the class that if they drew a flow net as good as that for a uniform soil, I'd be quite happy. Mine pillar, I'm Colorado School of Mines, so we do a bit of mining too every now and then. But I'm in a completely different department to the mining. Earth pressures, bearing, earth pressures, active and passive. Laterally loaded piles where the PY springs are random. And of course, slope stability. Here in this last slide, actually we have two simulations from a Monte Carlo set. I picked these because they look nice, they're interesting, but 2 simulations with very significantly different failure mechanisms. Both simulations have exactly the same mean, standard deviation, spatial correlation, showing that where the weak zones happen to be is where the mechanism will be triggered, and we will get the seeking out effect is shown very clearly. Spatial correlation is sort of shown in this figure as the width, the tendency for similar properties to be clumped together. We can do anisotropic as well, but I haven't got a picture here. An area of ongoing research, which I'm not going to dwell on today, but spatial correlation length is probably the least well understood of the properties you need for a risk analysis. And we have observed in several applications that there's a worst case spatial correlation length that leads to the highest probability of failure. This is very interesting because if you don't know any better, you should choose the worst case value to be on the safe side. I think it's a very significant finding that we'll revisit again in the future. Let me just conclude with a few comments. And fairly obviously, finite element methods remain the most powerful tools for modeling variable soils and for probabilistic analysis with variable soils based on a underlying statistical description. We've demonstrated a couple of sort of fun examples, if you like, for 3D and long slopes. And we asked how long was infinity. I digressed a little bit in the middle and talked about load and resistance factors. And we showed that resistance factors, dividing strengths by 1.3, let's say, is going to have a lot more influence on your result than multiplying the loads by 1.3. Designs are more sensitive to strength reduction, and this is why we've got the 1.5 for slopes and the 3 for bearing capacity in the textbooks. We have a whole toolbox of methods, and there's plenty of software out there, including if you want to play with some introductory ones on my website too, ranging from event trees, which are really much the state of practice at the Bureau of Reclamation and elsewhere, NGI, and right up to Monte Carlo simulations with finite element analyses that involve supercomputers. I mean, we have the whole gamut. We've indicated the worst case, and I haven't dwelt on this as much, but I just wanted to mention it, that this spatial correlation seems to be important in some problems. And as I mentioned, you can go to my homepage and grab any of these programs or contact me and I'll send them to you. One last piece of advertising. I'm chairing the GeoRisk 2017 conference in Denver in just 3 months, and less than 3 months, I suppose. And well, I hope to see you there. If you're interested in this topic, it's a great conference. State-of-the-art stuff will be on display, and we've got practitioners and academics on the keynote presentations. Thanks, Gary. That's about it.